you kind of find out that there is such a thing as too much grip on the car, where you're removing a lot of that wheel spin and the car will actually go slower.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Oscar from Zelaya Brothers in the US. Oscar is an ex-MoTeC USA employee. He's got a background in mechanical engineering. He's also got a strong interest in electronics, and he's used those skills both with calibration of engine management systems as well as the rest of the powertrain gearbox I'm talking about mainly here, as well as reverse engineering of late model factory cars. And this is a fairly wide-ranging interview. We talk about what is involved with reverse engineering a late model factory car when it comes to writing custom firmware and CAN bus communications to keep all of the electronic control modules happy. Later in Oscar's time at MoTeC, he got involved with Hoonigan, specifically helping out on Ken Block's Hoonicorn. We talk a little bit about the tuning elements involved with this, as well as its conversion from hill climb and gymkhana use to drag racing. We also dive into some of the intricacies of tuning on methanol fuel. We then talk about what it's like to start your own business, particularly when you are only 25. Oscar is really making a name for himself at an incredibly young age. On top of this, we dive deep into the topic of powertrain calibration in terms of what goes into calibrating a sequential gearbox, particularly around paddle shift. So a lot of information in here that I know is going to be interesting to a huge number of our listeners. Before we get into our conversation with Oscar, for those who are new to the HPA Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to tune factory and aftermarket engine management systems. We also cover performance engine building, wiring harness construction, race driver education, car setup, race car setup specifically, as well as data analysis, just to name a few of our topics. And you'll find all of them at hpacademy.com/courses. These are all online-based courses that you can take from the comfort of your living room. Specific to today's topic, and as I mentioned, it is quite wide-ranging, but we do dive into CAN bus a little bit. Now, this is definitely a very mature technology. There's nothing new about it, but in the last 5 to 10 years, we've seen aftermarket engine management systems really play catch-up, and the ability to integrate CAN messaging between both factory and other aftermarket electronics systems really opens the door for a lot of flexibility in our electronics package in terms of the products we're choosing and how we can make them communicate with each other. I know that a lot of tuners tend to get put off when it comes to CAN bus. It is not actually that difficult as long as you understand the principles and the fundamentals behind it. If you do want to learn more about what Oscar and I are talking about in this particular episode, you can check out our CAN bus decoded course. We will drop a link in the show notes to make it nice and easy for you to find. And as a podcast listener, you can use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. All right, enough of our introduction. Let's get into our interview now. Welcome to the podcast, Oscar. Thanks for joining us today. Now, your name actually originally came up during an episode with Sander talking about the Hoonipig, and given your involvement with Sander on that particular project, we knew we had to reach out and dive a little bit deeper into your story. For those who want a little bit of that background, we'll link to that particular episode of the podcast in the show notes. But Oscar, welcome along. Let's get started with a little bit of your background. So I'm interested, as always, to start by learning how you sort of got involved in the automotive scene to start with.
First off, thanks for having me here. It's an honor to be on this show with you. I got started early on with family. kind of like how a lot of kids with their parents, just repairing cars around the house. It turns into a hobby and get into trying to make your own personal cars fast and get involved with groups of people. And you start to learn about the motorsport community as a whole on a grassroots level. Okay, so at that point, what sort of cars are you personally tinkering with? They were S chassis, S13s. My first swap was a RB25 car, and that was what pushed me to wire it on my own. because I had paid somebody to wire it and they ended up falling through. So kind of turned into a lot of forums and reading about to make it happen.
So essentially self-taught with the benefit of the internet.
Yeah, I think being a part of the younger generation, we're really lucky to have the tools that we have available to us. It really expedites the learning process.
Absolutely. And obviously, our listeners don't have the benefit of video like I do here. And you're relatively young, Oscar. So let's just talk about that. How old are you right now?
So I am 25.
Okay. I think that's important because it gives our listeners a bit of a sense of where you are in your career. And as we'll talk about the success and what you've achieved so far, particularly at only 25, is pretty impressive and obviously paves the way for some massive future success. So credit to you there. Okay. So the S chassis, you've sort of alluded to there, you got involved in the wiring, which is fine. I'm assuming you're also actually doing mechanical work as well. That RB25 you mentioned, did you physically do that swap in terms of the mechanical side of things, not just the wiring?
Yep. Back in those days, you did everything. So it was a lot of the fab work, a lot of it in your garage, just trying to make it, make the mounts and make the intercooler brackets, get everything to physically fit in the vehicle and, modify it, taking these longer engines that are built for completely different chassis and trying to shove them in other cars. And back then everything was done. Just one person did everything.
Sure. I imagine that probably a lot of people listening that story will resonate with them. Very, very similar to how I got started, and no doubt the majority of people who have a passion in this industry. Let's talk about your actual formal education, though. Have you got any formal qualifications or education around the automotive industry in terms of mechanical or electrical work?
So specifically, I have a bachelor's of science in mechanical engineering, and following my time in academia, I went straight to the world of electronics.
Okay. So what drew you down that path? I mean, obviously there's a lot of crossover there with a mechanical engineering degree and what you can apply in the professional motorsport world. Was that what drew you towards that degree, or did you have different aspirations at the time?
At the time, I had a little bit of a different aspiration. I was interested in energy production, but then I got involved with the local school's Formula SAE program, and that kind of pushed me to a passion it was more of a hobby that became a passion. I became much more interested in it, working in a team environment and
Sure.
handling problems that people didn't want to handle is kind of how the electronic side of it came.
Okay, so the Formula SAE, I mean, it's something that I was always disappointed that I didn't get access to here in New Zealand through the university that I went to. I think that was a real missed opportunity for me, and I was always a little jealous of those universities that offered that. For those who have never heard of Formula SAE, could you maybe just give us a really quick rundown on what that competition is and what's involved?
So Formula SAE is basically building a scale model race car, not to glorify it. It is still a car built by a bunch of collegiate students, but it does give you the ability to tip your toes in the water of the motorsports world. And a bunch of different universities will come together and compete using these cars built by collegiate students against a given rule book.
You've kind of alluded to there that you got involved and ended up handling some of the electronics. Could you maybe expand on that? Was that your main focus with the team, or was it a little bit broader than that? Because obviously there's a lot that goes into these Formula SAE cars in terms of the engineering, the building, the construction, testing, and driving. But yeah, give us a bit of insight there.
So originally when I came to the university, there was no one wanted to deal with the electronics. So no one wanted to deal with any of the wiring. There was someone there who did want to do the calibration, but they didn't have a good understanding of the electronics. So when you have collegiate students trying to build a reasonably complex system, there's a lot of mistakes that can happen along the way. And if you don't have a good handle on the electronics, then your calibration is kind of quite poor.
In terms of that electronics package for the car, what did you sort of end up putting into it? What was the solution there?
So I was lucky to be local to MoTeC USA. So we ran a MoTeC M400 and a MoTeC C125 Dash.
Now, I don't want to jump too far ahead, but you did end up working for MoTeC USA. We'll dive into that in a bit more detail. Is that how that relationship sort of formed?
Yep. I was fortunate enough to be, there was a local professor who had existing relationships with MoTeC USA, and he saw that I had passion and the work ethic to push the project forward and that I was willing to learn. So I got the opportunity to work directly with MoTeC USA.
Well, let's pull it back a little bit. So after university, you've sort of mentioned your passion became electronics. So talk to us a little bit more about that path. How did that develop, and what did that end up becoming, and how long did that sort of go on for?
So as soon as I got out of university, I went to work straight for MoTeC, and there I was put in a position where you really have to have a solid understanding of the electronic package as well as the firmware package, because you're put in a position to help dealers. So with that, you're exposed to many unique problems, and the better you understand the hardware and the better you understand the firmware, the better job you can do to assist dealers who are actually out there pushing the product and putting food on the table for everybody.
Okay. This is probably an aspect that's reasonably specific to MoTeC, but just to dive into this, particularly, you mentioned there the solution for the Formula SAE car was the M400, which is an older generation of MoTeC ECU. Now their current generation at the time we're recording this is the M1 range of ECUs, which has been in existence still for a significant amount of time. But the unique aspect with that M1 range of ECUs is essentially the ECU itself, in terms of hardware, is just kind of a black box. And it's the firmware that is distinct to the hardware that then tells that black box what to do, basically the strategies and control functions that are within it. And MoTeC offer their own range of firmware solutions that are probably going to be suitable for, I don't know, maybe 90% of most mainstream projects. And then you've got the ability, if required, to use MoTeC M1 build to actually write your own custom firmware. So I take it you got deep into the development of custom firmware as well during your time at MoTeC?
Yes, I handled some of the different partner packages that were in-house at MoTeC USA. And I also got the ability to work with dealers on their personal partner packages and help them troubleshoot any errors that they're coming across or any erroneous behavior.
Okay. Let's just sort of define that term, partner package. What's that mean?
So partner package are bespoke pieces of firmware that a dealer or a distributor or MoTeC Australia themselves can put together to sell on an individual ECU. That way you can develop your own firmware that is application specific for whatever particular problem you're trying to solve.
So let's give an example of that. Let's say you've got a MoTeC dealer in the US and they solely deal with late model BMWs, just for example. I won't give a specific model, but maybe that's their bread and butter. They know it inside and out, and maybe they've been reflashing that car because there's no off-the-shelf plug-and-play solution for it, and then they see an opportunity in this market. We've got a lot of customers that want to modify the car and tune it, so they can develop their own M1 package, and that's going to be something that they will be able to sell for that car. That's how that partner package sort of works.
Yep, exactly. It lets you do a handful of things. For example, you can trim out the fat from a piece of firmware where you can make it more efficient in order to fit a lot of the what we would call OEM integration functions to maintain the rest of the car's functionality.
So I'm glad that you just brought that up, because this is the next point that needs to be discussed. Back when I first got involved with the aftermarket tuning industry, it was a simpler time back in the 90s, late 90s, maybe even the early 2000s. The cars we had access to were much simpler, and CAN bus really wasn't a thing, particularly in the 90s. We didn't have multiple controllers inside of the factory car that needed to talk to each other. That's all changed, obviously, and now that is the case. And talk to us about the complications of removing that factory ECU, fitting in M1, or for that matter, any aftermarket standalone, and having everything function. Where are the difficulties in that task?
So it's a little bit of a multi-step problem. Your first problem is you have to do a hardware by hardware analysis. So you need to look at what OEM ECU you're removing, and you need to look at what kind of hardware is inside that ECU that you don't have in an M1, for example. Things like onboard igniters, which are easy to solve. We don't have onboard Lambda, but you can use an LTC in line. After you handle the hardware side of things, you need to start looking at the security and the communications between all the modules. So when removing the OEM ECU, you have to keep in mind that ECU is having discussions with your body control module, your ABS, your TCM. All of those things need to be retained in order to keep the car happy.
So often, particularly in most mainstream cars, this relies on two-way communication over the CAN bus between those different modules that you've just talked about. So what we could do, essentially, providing that the hardware, as you mentioned, is capable in the first instance of even running the engine, what we could do is perhaps put in a run-of-the-mill production firmware ECU, get the engine running. But the problem with that is then the gearbox isn't going to change gear. Maybe the ABS doesn't function. Maybe the gauge cluster won't display anything. Maybe even the air conditioning won't work. Those are the sort of problems if we don't have full OEM integration, correct?
Yeah, I mean, even to the point where the vehicle won't boot up. You'll go to hit the ignition and nothing will happen because the BCM is waiting for an approval from what would be the OEM ECM.
Now, I just want to come back to a couple of the points you mentioned as well. You sort of glossed over that term LTC, which is MoTeC specific. So if you don't have an onboard wideband Lambda controller built into the ECU, which MoTeC don't, a lot of factory ECUs obviously do, you've got the ability to bring that Lambda into the ECU via an external module. LTC is MoTeC's Lambda to CAN. So basically it's a standalone controller that then sends all of the Lambda as well as diagnostic data over the CAN bus to the ECU. I wanted to clarify that. You also mentioned igniters. So if you've got a dumb coil which relies on an igniter, sometimes these are built into the OEM ECU. Again, MoTeC don't have that, as do probably a limited number of aftermarket ECUs. So you can get around that by using an external igniter module. So I just wanted to clarify those elements there. In terms of the actual process of this reverse engineering, basically figuring out what parts of the puzzle are missing and what you're going to have to generate, I'm guessing you can't go to the OE manufacturer and go, hey, I'm from MoTeC, I want to crack your car and figure out what's going on. Can you just give me all of that information? How does it actually work out?
So it's highly unlikely for you to get the ability to work directly with an OEM and get the CAN bus communication from them unless the OEM had interest in it in the first place. So if you are just a motorsport enthusiast and you're looking to integrate a standalone into a vehicle that you believe there's a market in, it's a pretty long process. A lot of people are way better at it than me, and it can take 6 months, a year, depending on the complexity. The cars are growing ever more complex. To reverse them, it requires a lot of what we call CAN bus sniffing, where you hook up something like a PCAN, which is a USB to CAN analyzer that you hook up to a laptop, and you can use that to log messages, and you can do specific actions in the vehicle to try and cause specific behavior that you can then come back and look at. So, you might rev the engine, you might break it in a specific pattern, you may turn it on and off a few times, capture startup messages, and you can start building a repository of repeated behavior where you can go back and start to identify the things that you need to mimic using the replacement ECU.
It sounds like an incredibly complex task. And I mean, I've been involved in some very low level, very basic CAN bus sniffing and decoding, and it can be a time consuming task. So the PCAN CAN sniffer, basically that allows you access to the bus so you can then see those messages that are being transmitted. And just to clarify, there's going to be a lot of information on that CAN bus, many messages on a wide range of different addresses. So it's kind of a little bit like maybe looking into the matrix, for example. And what you're talking about there is performing a particular action to try and highlight what addresses you're seeing a message change, correct? So you can sort of start zeroing in on where you should be looking for a particular thing that you're trying to decode.
Yes, exactly. Kind of like just trying to find a needle in a haystack. You're trying your best to identify that needle, getting a flashlight and trying to make it shine, trying to make something stand out from the barrage of numbers that you're staring at.
The other problem with this is, let's take something reasonably simple, like maybe throttle position. The numbers that we're seeing change in those canned messages, we're looking at 8 bytes of data for a message, and they're displayed in hexadecimal format, and you're not going to see something really straightforward that makes sense. So for throttle position, you're not seeing a number physically change from 0 to 100, are you?
No. So we have to keep in mind that computers don't recognize decimal points and they don't recognize units. So when these messages are being transmitted along the CAN bus, OEM engineers are quite clever in how they split up these messages in order to get the most out of a single message. So let's say you're trying to transmit throttle position, engine speed, temperature, or anything along those lines. You may have these divisors, is what we'll call them, or scale factors, where let's say you want to send 101.5%. Well, reality on the bus, if you try to send 101.5, you can't. You're either going to send 101 or 1015. So then you have to identify that 1015 is actually scaled by some number that you have to reverse out. And when it's divided by 10, it's pretty simple, but sometimes it's cut it in half, multiply by this, add this. So it's a combination of different functions, whatever the OEM engineer decided to do.
Yeah, I mean, particularly another good example there would be a temperature. So often there'll be an adder in there so that the raw number is never going to be sent through as a negative. And then when you apply the scaling factors, that then allows you to scale between a negative number, which we may see in the maximum positive, correct?
Exactly. And that brings into the fact that there are signed and unsigned values that can be sent, and that's identified by a single bit. So you either have to realize if it's a signed or unsigned value, or if they're using the adder to scale it, because it could just be offset to give you that negative scale, like you mentioned.
Sure. Now, I'm assuming that we don't want to go too deep onto this, but because we've sort of got this far, I just wanted to sort of mention for those who are wondering, well, how on earth are we ever going to work out what scaling factor to apply? I mean, often we're not completely blind here. You can use something like an OBD2 scan tool or the factory diagnostic tool to read as you're moving the throttle position. We've used that example already. You can see what the ECU is actually displaying in terms of throttle position. The scan tool will show that as a percentage that we normally recognize and understand. And then you can sort of see what that raw hexadecimal number is doing and see how the two change and work out the scaling from there, correct?
Exactly. So using some of those OEM tools, they give you a huge advantage.
Okay. Cars are obviously always continuing to evolve at the OE level, and the technology is becoming more complex, more advanced. A technology that I'm definitely not up to speed with, but as I understand it, is sort of replacing CAN bus, FlexRay. Can you talk to us about that? Is the aftermarket industry catching up with FlexRay? Where do you see that going?
So as far as I'm aware, FlexRay is going to be phased out, I believe, and it's primarily used by BMW. The German manufacturers are primarily using it. There are talks of new CAN bus specifications coming out from Bosch, actually, that are going to, right now, CAN FD is the one that a lot of OEMs are moving to. So it gives you much more, you can fit more bytes in a single message, and it gives you variable baud rate.
Yeah, okay.
The difficulties with FlexRay and why a lot of the German cars don't have standalone solutions like a lot of the newer BMWs is that FlexRay is a time-based protocol where each device understands who should be sending a message and when that message should be sent. So in normal CAN bus, devices, for the most part, are just blasting out messages, and each device is, accepting it and acknowledging it at the arbitration level.
Okay, so there's a lot more complexity in the timing of those messages with FlexRay.
Yes.
All right, as I say, we've probably gone a little deeper down that rabbit hole than maybe we needed to, but for 2% of the people listening, the real tech heads out there, that's probably pretty interesting to hear. Let's get into the core element here, though, which I wanted to talk about, which was your involvement with Hoonigan. Now, as I understand it from talking before we started recording, you actually started with Hoonigan while you were still working at MoTeC US on the Hoonicorn project. Is that correct?
Yep. So an old colleague of mine, James Whistler, he began the support for the Unicorn Mustang when it was first introduced. And he went into industry in a different position. And Hoonigan reached out and asked MoTeC if they had anybody that could come and support the project, as they were bringing the Mustang back out to do some. Brought it back out to do some drag racing.
Okay, so your involvement started after the Gymkhana and Pikes Peak sort of use of the Unicorn.
Yep.
I guess for those, I always make these broad assumptions that everyone listening is aware of these cars, and I mean it's been all over the internet. But maybe for those who are fresh to it, could you give us like a high level view of what the Unicorn is, specifically the engine and the electronics package, which is the interesting part from our angle?
Yep. So the Unicorn is a all-wheel drive, twin turbo, methanol, I guess you could call it, drift drag car, multi-use vehicle. It runs on alcohol, and it has two 1700cc injectors per cylinder, and it runs on an M150 alongside a C125 logger and a PDM 30.
Okay. Coming back actually one step, I mean, I don't know if it's particularly usual across the industry for the aftermarket ECU supplier or manufacturer, in this case MoTeC as it is, to actually do direct support for customers. Is that unique to MoTeC, or am I missing something here? Is that quite common? No, what I'm getting at here, I guess, is normally someone will go to a MoTeC dealer. That MoTeC dealer will supply the electronics, do the installation, and then the calibration, rather than the team coming direct to the manufacturer.
So the Mustang is quite old. So when it was first put together, it actually was an early on, in my opinion, still in the infancies of M1 and the firmware. And I think MoTeC wanted to control the aspects of it to make sure that it was going to go well. And it has gone well. For the most part, it ran generic firmware up until right after the Gymkhana at Pikes Peak.
And by generic firmware, what you're meaning is production firmware that basically anyone could get access to. None of this custom stuff that we've sort of alluded to already.
Exactly. It was basically a run-of-the-mill. You could go to any MoTeC dealer and replicate that exact same setup between your power distribution, your display logger, and your ECU.
All right. It'd probably be interesting to talk a little bit about some of the changes that were required going from a setup for the likes of Gymkhana, Pikes Peak Hill Climb, and Gymkhana use to drag racing. Tell us what actually needed to be changed. What did you sort of get involved with there?
So some problems that actually arose is that when the vehicle was starting to be used in terms of launch control and actually launching the car, preparing it for drag racing, we ran into some crank trigger issues. I believe it was exposed due to the ignition system not being used that way before. We ended up finding out that in particular on this vehicle, the spark plugs needed to be swapped out for resistive spark plugs. And that's not always the case. It's kind of on a case-by-case basis. A lot of people can get away with non-resistive plugs. In this situation, we had to use resistive plugs.
It's interesting you say that. In the past, where possible, I always, as a matter of course, will choose a resistive plug. And I guess really, I'm not an electronics engineer, so maybe you can give us a little bit more insight into this. As I understand it, non-resistive plugs essentially can create a lot of RF interference in and around the engine bay, which is less of an issue with a resistive plug. But I've found that some brands of ECU, and I won't name names, seem to be much more sort of sensitive to that element than others. And I mean, there's been cars which I literally could not run on the dyno with non-resistive plugs. You swap to resistive and they're fine. A different ECU brand and it really seems to make no difference. Can you give us some insight into that?
I think a lot of it comes that the M1 architecture is pretty special when it comes to the way that the crank trigger is handled in terms of, I can't really get too deep into it, but just know that it is well thought out. There's dedicated pieces of hardware to handle a lot of what we would call, your ref and your synchronization. So your crank, your cams. The Australian hardware engineers have worked really hard to develop a robust solution that, in my opinion, you only see in high-level ECUs like, Bosch Motorsports or McLaren.
I think it's worth just mentioning that how critical that the reliability and the robustness of that information is to the ECU, because that crank signal is giving us engine speed, engine RPM, and then we've got normally a synchronization input as well, giving us whereabouts in the engine cycle the engine is at any time, and essentially everything else that the ECU does, all of the fuel and ignition calculations are all based on that information being reliable. So it really is the very ultimate case of garbage in, garbage out. If that information isn't robust and reliable and accurate, then basically we throw everything else out the window, right?
Exactly. And the ability that MoTeC allows and a lot of the high level ECUs allow for you to filter and create these safety windows for what should my voltage be at this engine speed, what is what we call debounce or filter time, and setting up thresholds for pitch. So, a lot of the newer vehicles now are running what 60 minus 2. So you'll have 58 evenly spaced teeth, and then 2 will be missing where the other 2 would have gone. And understanding the period between teeth and knowing if you missed a tooth or not is very important to running the engine and maintaining that robustness.
Sure. I'm interested also to talk in more general terms about the launch control strategy that you were applying on the Unicorn. I mean, I come personally from a background of drag racing, and for those who are not into drag racing, it seems like a very simple task. You accelerate in a straight line for 400 meters. I mean, what could be more simple than that? Obviously, when you're starting to make 1,000 plus horsepower, there are a few complexities that creep in, but essentially the key to drag racing is all in the whole shot, how quickly you can get to that 60-foot point. And the sort of the golden rule of thumb has always been that if you can gain a tenth to the 60-foot, that sort of within reason is 2/10 at the 400 meter mark. What I'm getting at here is getting that launch absolutely on point without excessive wheel spin, but without the car bogging down, is critical. So can you talk us through the launch control strategy that MoTeC employ in that ECU and how you are utilizing it?
So on the Unicorn, it presents a little bit of a special problem because it's all-wheel drive. So your ground speed reference is not great. This was before I knew that Sandra was developing his INS. So his INS has come and turned the world upside down, in my opinion, that, you can now have a really good ground speed reference that you had to fight before. So on this particular car, a lot of it is time-based. So, you're doing a lot of time-based calculations at the drop of your launch switch or clutch switch. And you kind of find out that there is such a thing as too much grip on the car, where you're removing a lot of that wheel spin and the car will actually go slower. In the case where you're bogging it down and it can't come up on the clutch, or you're just finding the limitation of the tire and what the engine can provide.
And the sort of theory as well, I mean, it's hard to put a across the board answer because it's going to depend so much on the particular tire, but we actually get a maximum grip from the tire with a certain percentage of slip, and by that I mean wheel spin. Generically, probably somewhere around about sort of 10% is the number that's normally thrown around. So we actually want to keep a little bit of wheel spin, but of course, initially as well, if we mapped engine RPM versus ground speed, and you had just a direct one-to-one correlation, obviously at zero ground speed, which is the point where the car is going to leave the line, you would also have zero RPM, which clearly isn't going to work. So there's sort of initially got to be some blend of having enough RPM on board to get the turbos to spool, to have enough torque to actually spin all four wheels. And then, you don't want to just sit there on the rev limiter because it's just going to go straight up in tire smoke. So are you talking here with the timer base, basically an RPM limit that is relative to a timer? So you're trying to sort of match the RPM to wheel speed as the car gets out of the hole in first gear?
Yes, but we do it more so in this particular instance on ignition timing reduction and throttle curve. So because it's drive-by-wire, it gives you the ability to control that throttle. With the engines that produce a lot of torque and they have a lot of boost on the backside of the throttle, small movements in throttle can translate into wheel spin just from rapid increases in torque. So being able to control that throttle and use ignition timing and blend it in as the vehicle gains wheel speed is pretty useful. So you can maximize.
In terms of the sort of launch limiter when the car's actually stationary, we can also use ignition retard to help build boost. A lot of this comes down to sort of the sizing of the turbos versus the sizing of the engine. As the turbo gets bigger relative to engine capacity, we physically need more exhaust gas energy to help drive the turbo and create boost. Not such a significant issue with smaller turbos on bigger engines. So is that something you're utilizing there, or not such an issue on the Unicorn?
It's not a huge issue. We use a small amount of ignition retard and some fuel just to increase that flow through the turbine, and that helps bring it up pretty reasonably. And because of it being a large displacement engine, it's able to build boost pretty reasonably.
Okay, sure. One other element that I wanted to talk about is just some of the specifics around tuning for an alcohol-based fuel, methanol in the specific example. I mean, these days, alcohol fuels in terms of ethanol, E85 particularly, it's kind of like the go-to choice for most performance applications, particularly turbocharged engines, because of its properties. Methanol has long been the choice of drag racing, particularly blow-in turbocharged engines, again, because of its properties. So can you talk to us about some of the differences maybe with tuning on a methanol-based fuel versus gasoline or even E85? What's your sort of mindset shift have to be?
So on a methanol-based fuel, you're pretty lucky. You get to play with a fuel that is highly resistant to detonation or knock. It allows you to have a wide safety net when it comes to ignition timing. Now, the caveat to that is that methanol is very susceptible to being erratic when ran lean. So you have to be very careful on not running it too lean. If anything, you always want to start off with it richer than what you expect, and you can back off on it a little bit. You also keep in mind, though, many of the people who run alcohol may not run an intercooler. And to overcome the fact that you're not running an intercooler, that may require you to run a richer mixture to take advantage of the latent heat of vaporization of the methanol, the amount of energy required to take a liquid fuel and turn it to a vapor. The methanol does a great job at removing that heat from the air charge.
Yeah, I'll just talk about that term you just meant, latent heat of vaporization. So essentially, as you inject that fuel, it goes into the cylinder, it goes through a phase change from liquid to vapor. And as it goes through that phase change, it absorbs energy, and it absorbs that energy in the form of heat. So it has the effect of massively cooling our intake charge, correct?
Exactly.
And then, as you were saying there, a lot of people take advantage of not running an intercooler on methanol, and thereby, if we run a richer mixture, inject more fuel, we've got more of that cooling property, that cooling effect going on. Now, the other element you mentioned there, sort of, it's not very tolerant of a lean mixture. And this is one of the things I find with gasoline versus methanol fuel. With a gasoline-based fuel, within reason, as we go richer, and particularly there'll be a point where we sort of fall off a cliff, we end up seeing that power curve drop away quite sharply. So, for a turbocharged engine, we might be talking, richer than maybe 0.75. We're going to start to see a pretty sharp taper off in our power, and we go much richer than that. We're probably going to get to a point where we just can't reliably ignite the fuel air charge. Obviously, that's ignition system dependent. So we kind of end up playing this sort of game where, within reason, the leaner we run, the more power we make on gasoline, and there's sort of this happy point where the engine's going to be reliable, we're not prone to knock occurring, and we're making good power. On methanol fuel, if you apply that same mentality, you're probably going to end up in a world of hurt with a bunch of melted components. The flip side of methanol, as I've experienced it though, you can run it excessively rich, just pour the fuel in there, and you see little to no drop off in power. Does that sort of match your experience with the fuel?
Yes. Obviously, you can go ridiculous, and it's really dependent on your ignition system. You have to make sure that your ignition system can keep up. I've found in my experience that with methanol, you have a little bit of a sliding scale between power and lambda. So as you start increasing the amount of power per cylinder, or the amount of torque per cylinder, let's say, you have to start running a richer mixture, just because of the amount of power you're trying to make per hole. So, on a motorcycle that's turbocharged on alcohol, we might be running a 0.68 or zero point 0.7 lambda. And then, we start getting into these 2000 horsepower pro mods. You start approaching more of a 0.58, 0.55, 0.6 lambda.
Yeah. I'm glad you mentioned that, because I just wanted, that was going to be my next question, is just getting a sense of where we are on that lambda target. I mean, for anyone who's tuned on gasoline, these numbers, as soon as you're talking the 0.5s, wow, that's just, you're in a different ballpark. But I mean, I think we also need to understand the properties of the fuel. For a start, if we look at the stoichiometric air fuel ratio for gasoline, obviously we're 14.7 to 1, methanol 6.4 to 1. So you're very different stoic air fuel ratios out the gate, plus those other properties allow us to run richer as well, correct?
Yes. And with running that rich, you have to make sure that you're running sensors that can handle reading that kind of lambda. You can't use these LSU 4.9s when running alcohol at these extremely rich mixtures.
It's like you're reading my mind, because that was going to be my very next question. So how do we get reliable data in? A lot of these sensors will, if you look at the spec sheet from the manufacturer, the LSU 4.9, if my memory serves correct on Bosch's specifications, is a minimum lambda of 0.65. So obviously in a Pro Mod engine, you're melting parts of that. So what's the solution there?
Yep. So the industry standard, as far as I'm aware, and what I've used for the most part, are NTKs. So NTK lambda sensors are what most anybody uses on an alcohol engine. That's what we use on the Mustang, the Unicorn, as well as the Huna Pig, and a few other high power projects that we've been involved in.
And MoTeC just provide a different version of the LTC. Actually, I think it can be reprogrammed, can't it, between LSU 4.9 and NTK? Or is it a different unit? I can't quite remember.
For the MoTeC side of things, it is a different unit. There are a few other wideband products out there that are apparently support both, either an LSU or an NTK. But for the MoTeC side of things, you either get an LTC that supports an LSU or an NTK.
Yeah, okay, thanks for clarifying that. And just sort of another part that goes into this, and in my experience back when I was running a tuning shop, and back then this was pre 4.9 lambda sensors, probably give you some sense of the generation there. So we were using the older LSU 4.2 sensors, and particularly I was tuning at that point a lot of cars running on leaded fuel such as VP Racing C16, Q16. Sensor life in that environment was very limited. I think my worst scenario was tuning a drag car. I went through a brand new sensor in about 20 minutes of tuning, and we actually switched at that point to the NTK sensor. And even tuning these leaded fuels, the sensor seems much more robust, even though it is a little bit more money. I mean, we were getting 12 months on a single sensor. So I just wanted to point that out, that the sensor life is a really big factor, particularly if you're a professional tuning shop. I mean, going through a LSU sensor once a month or more frequently versus once every 12 months, that's a massive difference. Moving on, at this point, you're still working directly for MoTeC US, but supporting the Unicorn. And at some point, you've actually decided to go out on your own and start your own business. I'm interested in sort of learning a little bit more about how that sort of seed got planted and what you wanted to do.
So I was originally presented with an opportunity to help a medical startup while I was at MoTeC. And I took the leap to become I was leading a hardware development project with this medical company. And being that it's a startup, it was a little volatile. So it was getting to a rocky place, and I was still being contacted by people that I had helped when I was at MoTeC, Hoonigan included. And I was fortunate enough to be put in a position where I was needed for the next 8 weeks in terms of support and, just being on site and being able to charge. So I took the leap of faith that if I can pay the bills for the next 2 months, we hope for the best afterwards. And so far it's worked out.
So you sort of leapt out of the plane and built the parachute on the way down.
Yeah, exactly.
That's 8 weeks of support. How long ago was that? So we've got a bit of a sense of scale here.
A little bit over a year ago, maybe a year and a half ago.
Okay, so what's your experience been in that time? What have the challenges been of keeping yourself busy, keeping income coming in, putting food on the table? What are maybe the challenges or aspects that you never even saw coming when you decided to take that leap?
So the biggest one that I think a lot of people don't realize is the cash flow problem. Yes, you may have work for the next 10 weeks or the next year, but that doesn't necessarily guarantee cash flow in the next 30 days or cash flow in the next 90 days. You have to manage whatever funds that you have in order to maintain the business and or your personal finances, where a lot of companies, once you start dealing with larger companies, they want 30 days to pay, 90 days to pay. And these are things that sometimes you have to suck it up and deal with it, or sometimes you can kind of twist the arm and make it happen sooner.
Yeah, so and that probably sounds like a pretty bizarre situation for those who haven't been in business, but essentially the process for a lot of these companies is you do the work, you submit your invoice probably at the end of the month, and then you just patiently sit there waiting for the money to come in. And at least in my experience, maybe yours has been different, I find that often that also required maybe 2, 3, or 4 sort of gentle reminders, sometimes not so gentle reminders. Hey, guys, I'm starving here. How about you pay me? Is that sort of how it works out sometimes?
Yeah, especially, the fact that I'm young and I'm learning a lot of this. I'm generally the youngest person everywhere I go. So just sometimes it requires a little bit fighting, fighting for yourself to show that you're serious and you mean business about, the profession and the kind of work that you're doing.
It's a really good point that you raised, because I think at the start of my business, STM, I was probably maybe even a little younger than you are now. And I found the age thing to be quite problematic, at least with new customers. And I'm interested to hear your take on it. I mean, rightly or wrongly, I think there's an expectation that knowledge and ability is correlated directly with age. I mean, obviously that's absolutely ridiculous within reason, but that's sort of the perception that the industry has. How much of a problem have you found that?
For the most part, because I've been fortunate enough to work with many high-level people, I've had a lot of high-level individuals in the industry vouch for me. So that's placed a tremendous amount of stress on me, but it's given me the opportunity to work with some high-level projects, and people kind of respect it off the bat. I don't necessarily go walking around telling people that I work on these high-level projects. So when a new customer does come, and I had somebody show up at the shop, and they're like, "Well, hey, where's Oscar?" And I'm like, "I'm Oscar."
I suppose your resume in terms of the project you've been working on, though, speaks for itself. And I mean, ultimately, if you're knowledgeable, you've got the runs on the board, it is what it is, and the age should not be a barrier to entry. I only raise it because I know, at least in my experience, I wouldn't say it was a barrier to entry, but it certainly at the start of my career, there were a few raised eyebrows until the customer actually understood that I knew what I was talking about and I could do the task. In terms of some of the other elements of starting and running a business, and I think a lot of people, particularly when they're maybe a solo operator, they get into business because they're good at a task, tuning, calibration, whatever it may be, and then they quickly realize that the working day only allows them to do, maybe 50% of that task, and then the rest is all of the other business operation elements, the administration, the emails, dealing with customers, maybe advertising. And that can, for a lot of people who maybe don't enjoy that element of business, can be a little bit daunting, maybe a little bit off-putting. I'm interested to learn how you've found that.
So the number one thing that I've learned and that I was really poor at, and I made a mistake with the customer before, and that's managing expectations. Being able to manage someone's expectations and give them an understanding of where the project is going, what the process from start to finish looks like, is one of the most important aspects, in my opinion, to maintaining good customer relations.
Yeah, I think that's a fair point. Particularly for customers, they probably, if they haven't been involved at this sort of level before, will have no idea of the process. So I think getting expectations aligned at both sides is going to make for a smoother process. And if you've got that aligned at the start as well, I think if there's going to be problems with maybe timeframe or budget, those get discussed and dealt with at the start, rather than 2/3 of the way through the project where it's very difficult to come back from that. Is that sort of a fair point to make?
Yes, exactly. And working at MoTeC, I got wonderful opportunities to work with OEMs and, get my feet wet with talking with high level individuals within a corporation, for example, and understanding how to explain from start to finish how the project might go, what the funding needs to look like, and what the support plan may look like after the project is finished.
In terms of getting work, getting customers through the door, are you doing anything in the way of marketing or advertising at the moment, or is this purely word of mouth based on your existing sort of network of people that you've dealt with through MoTeC?
For the most part, it's been word of mouth. We don't really do any advertising or anything like that. I've just been lucky to work, with a awesome network of people, and I have people who trust me to take on work that they are too busy to take on. Some high level names that, I'm really grateful for to be in the position that I'm in.
I should mention the name of your business, Zelaya, if I'm saying that correctly, Brothers.
Yep.
Did I get that right?
Yep.
That would insinuate more than one of you, correct?
Yes, you're correct.
And what's your brother doing?
So my brother is 21, and he is learning the ropes for data acquisition for right now. He's doing a lot of data analysis. So he's running what we would call, he's the DAG for a sports car team. So, just to give a quick rundown, the job and the responsibilities of a DAG is to handle the electronics of the car as well as the data from the car, which means, post-session, pulling the data from either a MoTeC logger, Magneti Marelli, VBox, a combination of different electronics, providing it to the race engineer and working with the race engineer to decide on what changes to make for the vehicle.
Okay. We could talk probably for a whole podcast just on that element, but I'll keep it to your story. I just wanted to sort of get a bit more of a sense of what Zelaya Brothers actually entails. So good to get that. Let's get into the Huna Pig or Huna Pig Assist. I still can't really get my mouth around that. So this came after you had parted company with MoTeC, and you were involved here with Sander, our past guest. So can you maybe give us an understanding of what your involvement and responsibilities there was?
So my responsibilities on the Huna Pig was to manage the engine and the gearbox. So anything related to the engine in terms from anti-lag, traction control, gear shifting, and any of the driver aids were under my responsibility.
Okay, and Sander was a more sort of high level, the initial electronics specification, design, harness construction, initial calibration, etc. Correct?
Yep. So Sander did a lot of the initial system design, and then he also went along to manage the rest of the chassis, I would say, while we were running the car.
Now, obviously, we've dived into that side of things with Sander. So I want to maybe talk a little bit more about the areas that you were specifically involved with. We've talked calibration off and on throughout our podcast. Maybe we'll get into some of that, but an area that we haven't dived into at all so far, and one that I think there's a distinct lack of information, is around gearbox calibration. So I want to sort of go a little deep on that, and people might be sort of thinking to themselves, well, what the hell is gearbox calibration? It's a mechanical device. Surely it is what it is. But obviously these days we have sequential transmissions, and then as in the Huna Pig, you've got a paddle shifted transmission. I think to get a sense of an understanding of what we're trying to achieve, we probably need to start with the basics of how a dog engagement transmission works. Now, obviously, we don't have the benefit of a nice, simple illustration on a podcast, but could you do your best to give us an understanding of how a dog engagement transmission actually functions?
So the dog engagement, you can kind of think of it almost like when you would fit shapes into little holes as a toddler, maybe, where you would fit a triangle inside of a triangle hole. You have these blocks on a gear assembly that fit into a receiving end of another gear assembly. So when you go to make a shift and you move the forks, instead of there being a synchronization, there are these blocks, or what we call dogs, that are aligned with a receiving end on the other gear set.
Yeah. Okay. Yeah, I think that's probably a pretty good understanding. So basically on the gear itself, we've got these blocks, as you mentioned. Think of it as a castellated nut in a way. And there's big windows or gaps between the adjacent dogs. And then you've got the selector, which also has matching dogs. So when you select a gear, those slide together and kind of lock in place. The key element, though, is, or one of the key elements here, is that these blocks are not square. They've actually got a slight back cut. So the idea there is when they're engaged and you've got torque being transferred, the torque kind of locks them together. You could apply as much force to that gear lever if we're talking a conventional mechanical sequential gearbox as you like. There is no way you're pulling that thing out of gear. So now that we sort of understand what's going on inside the box, tell us what's required, the process of maybe an upshift. Let's start with that.
So on an upshift, you need to, I guess, to start with just the mechanical side of it first. You have to, what we call, disengage the dogs. And in order to disengage them, you need to do a torque reversal on the engine. So you need to do some torque reduction, either by way of ignition cut, ignition timing, or fuel cut, before you're able to move the selector and move on to a different gear set.
Okay. And I mean, if we go back one step further, in the earlier days before gear change, ignition cut, or these shift strategies were around, I mean, you could mechanically do this as the driver, and you'd sort of come up to the shift point, apply a little bit of force to the lever. As I mentioned, it isn't coming out of gear, and then all it would require at the shift point is just a light lift on the throttle, and that was the driver mechanically reducing that torque, providing that torque reversal. Correct?
Exactly.
All right. So the options available for that torque reduction, you've kind of just mentioned there, ignition cut, ignition timing, retard, fuel cut. I mentioned, obviously, the lift of the throttle. Pros and cons of those options, why you'd choose one over another, why you'd maybe choose a combination?
So a lot of it is going to be dictated based on how much torque you need to reduce, how much torque is the engine making, and how much do you need to remove in order to get the dogs to disengage. My personal preference on an upshift is ignition timing. It tends to be softer. It tends to be less of an intervention on the driver. The downfalls of using something like, let's say, ignition cut, for example, is that you could still have erroneous behavior in the combustion chamber that will then cause issues with the valve train if the valve train is not particularly stiff. For example, like we talked earlier on SR20s, they have a rocker shim assembly. So any play in that assembly can give you a really hard time where the rocker now has too much clearance as the shim has popped out.
To sort of go deeper on that, this is a real problem with a lot of valve trains, where particularly if there's a shim or a rocker, what we sort of end up with a situation where you use an ignition cut, it's really no different to a launch control two-step anti-lag strategy, where we're cutting the spark to a cylinder, but we've still got a full cylinder's worth of unburned fuel and air that's passed through there, where it can ignite and combust in the exhaust manifold. So that's the anti-lag strategy. We're purposely trying to do that to drive the turbocharger. But the upshot of that is we're going to end up with pretty significant and sharp pressure spikes occurring in the exhaust manifold, the exhaust system. Those can be enough to overcome the valve spring pressure, essentially popping those exhaust valves back off the seat. The upshot of that is we then get this loss of control between the rocker and the valve, and that's where things sort of can get nasty. That's kind of what you are pointing towards?
Yes.
And when that happens, generally it's going to end pretty poorly. And this really comes down to the same can be said of the rev limit strategy that we want to use for exactly those same reasons. So, okay, coming back to the control strategy. So you do need to have an understanding of the particular engine you're calibrating and how you're going to go about that based on that valve train, right?
Yes, sir, exactly.
Okay. What sort of time period are we talking with this torque reduction, torque reversal? Or is it dependent on the particular gearbox?
A little bit dependent on the gearbox, but you can have a shift happen in 40 milliseconds, 50 milliseconds, 100 milliseconds. It kind of just depends on if it's a paddle shift. On the lever shifted transmissions, you have a little bit longer because you're reliant on the force of the arm of the driver. So a lot of the latency and the driver reaction and them preloading the dogs before you hit it with the torque reduction, and then them moving the lever to actually select the following gear.
Okay, so that term you just used, preloading, so that kind of comes back to what I was saying. If you're the old school style with no electronic intervention, you'd tend to pull on that lever to preload, as you say, the dogs, and then do your torque reduction. If we're looking at a conventional, a modern, I should say, paddle shifted gearbox, where you're using maybe air pressure to create the shift, are we still able to do this preload, or is there an advantage in it, or does it not really matter?
Yep, there's an advantage in preloading. Normally, you might use a 5 to 10 to 15 millisecond preload where it's a combination of handling the dead time of the solenoid and filling the RAM with air, as well as then physically loading the dog.
Okay. So essentially then when the torque reduction is instigated, we're going to get an instant movement of the selector as opposed to waiting for that latency that you've just mentioned.
Exactly.
Okay. Now, another term that's thrown around with these gearbox control strategies is closed loop. And this is where we're sort of able to go a little bit more granular on our level of control. Can you talk to us about what that closed loop actually means?
So closed loop is monitoring of the barrel position. So you're actually monitoring the movement of the barrel in the gearbox that lets you know, hey, I'm in first gear, second gear, third gear. What closed loops lets you do is that you can run an extended amount of shift time, but the torque reduction and or the shift strategy will recognize once you're in the next gear and immediately end that shift process.
So you could set up maybe a 150 or 200 millisecond torque reversal, but that torque reversal will actually only be as long or as short as it needs to be until that next gear is detected to be completely engaged.
Exactly. But the caveat is that if you do have a sensor failure, then you will have to resort to running open loop. And if you have an extended amount of shift time, you're now bound by whatever you have programmed in the ECU.
So we still want realistic numbers in there. We're not going to program 1,000 millisecond because, as you say, if you've got that sensor failure, you're going to have an incredibly slow car.
Yep.
Now, the benefit there, though, is that the shift is always going to be as short as it can be. And I mean, you might expect that every shift is going to take the same amount of time, but depending on a number of factors, that might not be the case. Prior to closed-loop gear shift control like this, we had time-based, where we sort of had to put in a sensible value that was long enough for the shift to complete, maybe 100 milliseconds, for example, and the shift has actually completed in 60 milliseconds. So we've got 40 milliseconds of wasted time, but it's kind of just a necessary evil in that style of system. So suffice to say, a closed loop control system properly set up will be faster around a lap than a time-based system.
Yes, will be faster and easier for a novice to set up because they can start with higher values that may not be necessarily true, and then use the closed loop to help tune it in the same way you would an efficiency table.
Okay. In terms of the effect on gearbox reliability and gearbox life, before any of these control strategies were employed, you'd have a mechanically shifted dog box and two drivers that may be equally fast in terms of outright lap time, and one driver might get a season out of the gearbox with no real sign of wear on these dogs, and the other driver might be chewing through a couple of dog rings per race meeting. The reliability of a closed-loop control system like this, what's it sort of do to the gearbox life and reliability?
It extends it in terms of being able to identify when the torque reversal has to stop, and then you can kind of reintroduce torque at a given rate. When you do the torque reintroduction, you can control it so that it's not too fast or too erroneous. The ability to identify dog clashes, I would say, are just better because you're able to monitor the barrel position fast now. So when you do have issues where you have a dog-to-dog event, you can kind of find this in the data and use this to your advantage to help you fine-tune the gearbox strategy.
Okay. I'm guessing that just with everything that's happening so fast, dog-to-dog clashes are just a reality and sometimes unavoidable, or is it something we can try and tune out with our calibration?
Sometimes you can tune it out. If you're doing poor timing with the preload, maybe you're excessively preloading the dog and you're waiting too long to do the torque reversal, or maybe you don't have enough manifold pressure in the plenum to aid in the movement of the drivetrain as you go to reintroduce the torque. All these things can affect how the gearbox reacts to the torque reduction and reintroduction of torque.
Okay. It's like you're reading my mind here, Oscar. So a couple of things you've just talked about. So the torque reintroduction, that's the next thing I wanted to talk about. And then you've mentioned manifold pressure, which we'll get to as well. The torque reintroduction. So after the change is complete, on face value, you'd think maybe we just want to be back to the maximum torque that the engine can produce as quickly as possible so we can start accelerating at the fastest rate. That's not always the case?
Not necessarily, especially if you're on the limit of the box. If you massively increase torque at a rapid rate, you could hurt the box as the dogs slam into engagement point, as well as you have to think about it from the whole chassis perspective, where you don't want to upset the vehicle by reintroducing 400 foot-pounds or whatever we're going to call it of torque and induced wheel spin, which then will push you into your traction. And these are all things that either slow down the car or can just highly upset the car on a gear shift.
I think the other thing that's important to mention there is, depending on the inertia in the engine itself, when we're upshifting, we need to pull the engine RPM back down. So obviously it's gear ratio dependent, but we might be needing to reduce the engine RPM by 1,000 RPM. And if you've got an engine that has a lot of inertia built into it, it's not going to be able to change 1,000 RPM, reduce 1,000 RPM in 10 milliseconds necessarily. So that in itself can sort of, you're almost using the drivetrain to pull that engine speed back down, correct?
Yes, taking advantage of the fact that you can use engine braking to help you with the gear shift.
Okay. So the torque reintroduction, if I'm sort of getting a sense here, it's going to be very much chassis dependent and gearbox dependent. There's no sort of magic golden numbers that you'd apply to every scenario.
Yep. So very specific to the gearbox, the tire, the chassis, how stiff is the chassis, what does the tire look like? On the Mustang, for example, we are on the very edge. Well, we're beyond the specification provided by SADEV. So when we drag race it, I try to be pretty lenient on the gearbox just because the torque that engine produces is pretty high. The one time that we did try to really lean on it, it split the input shaft.
So that's the old push it until it breaks and then back it off a touch technique.
Just a bit.
Yeah. I mean, if you've got budget, that unfortunately is also a completely valid way of finding where those limits apply. Talking about the rest of that upshift strategy, I mean, I know in the MoTeC you've then sort of got a rearm period as well. Can you talk to us about what that means and why that's there?
So the rearm period is that you don't want to excessively accept a paddle shift request once a gear shift has happened. So if a gear shift has happened and let's say simultaneously the driver runs over a quite rough part of a track and bounces off the paddles, you want the ability to ignore that because a shift just happened. You would say it's obvious that you shouldn't be shifting right after a shift has just finished.
What sort of numbers are we talking here? Sort of maybe 500 milliseconds, 1,000 milliseconds?
Say something like quarter of a second. So, 200 milliseconds, 200 to 300 milliseconds is probably reasonable.
All right. I think we've got a reasonable sense on the upshift process now. Let's look at the flip side of this with the downshift. And again, talk us through for a start the process from being in a gear and needing to downshift. So the dog's already engaged in, let's say, third, and we're going down to second. What do we need there?
So number one thing is that you're off throttle and you're in an engine braking state where you're coming into a corner, you're letting off the throttle, and now the engine is decelerating. You need to do a torque reduction, and then you have to blip the throttle in order to increase the engine speed and prepare it to enter into the different gear set, because your engine speed is going to increase as you're coming to a downshift.
So again, conventionally, we would be doing this. The driver would be manually blipping the throttle. As you say, you're braking, so this is sort of heel and toe, and most drivers with a sequential transmission still use the clutch, but not always. Some left foot brake and just manage to time that blip to absolute perfection as they're slotting it through the gears. These days, though, with drive-by-wire, that's not a consideration, particularly with paddle-shifted boxes where we're using the drive-by-wire to do that blip. And before we kind of continue down this path, I think it's a good point to just pause and talk about drive-by-wire. Every time we post anything on our social media about drive-by-wire throttle, we inevitably get the cable throttle brigade sort of up in arms about how drive-by-wire throttle, A, is unsafe, B, unreliable, C, it's too slow and laggy. Can you debunk any of that? What's your take on this?
So from a safety perspective, when this was first introduced in the OEM world, there's a lot of redundancy placed with dual standalone sensors within the pedal as well as the throttle body itself that monitor. We would call this main and tracking in MoTeC world, where you have a main position sensor as well as a tracking position sensor. And these values are referenced against one another to make sure that you're getting the exact type of behavior you want out of the throttle body.
So in other words, we've got fact checking at the throttle pedal, and we've got fact checking at the throttle body itself to make sure that essentially both are doing what the ECU thinks.
Exactly. And these sensors are separated from a hardware level in most applications, where if one sensor does fail, it will not affect the other sensor.
Okay. On top of this, obviously, that's great if they're both doing what they should be doing, but we still have the potential situation where the driver's asking for a commanded throttle body opening of maybe 82%, and instead it's at 100%. Now, that would probably be the concern for most people looking from the outside at drive-by-wire. So if by some sort of weird situation that happens, have we got a safety strategy in place to deal with that kind of scenario?
Yep. So even most standalones have a safety strategy where you can employ a low engine speed limit in order to basically allow you to limp the car back to the pits or wherever you may need to go.
All right. I think that deals with the safety concern. Basically, there isn't one. I've been dealing with drive-by-wire throttles for as long as I can remember now, and I've had more trouble with cable throttles failing or giving trouble than I have ever with drive-by-wire. The lag or sponginess of a drive-by-wire, let's talk about that a little bit.
So I think a lot of that myth, or I would say a lot of that ideology, came from the earlier days of the introduction of drive-by-wire, and even more so the introduction of drive-by-wire to the aftermarket community. A drive-by-wire motor is not necessarily highly complex, but it does require a reasonably robust control strategy to make sure that what you're commanding is repeatable, because this is a spring mass-based system, so you're always fighting against a return spring. So the PID becomes just a little bit complex, and in the beginning of the introduction of drive-by-wire, not only were the motors a little bit archaic in the amount of torque that they would produce, but the control strategies were also more archaic. In modern electronics now, the response is quite good. And I think a lot of times people confuse the lack of response of a drive-by-wire throttle with actual engine transient. There are some of these things like your fuel timing and your transient fueling requirements need to be pretty well dialed in, as well as your efficiency table, in order to make the engine be snappy and responsive. It may not be the fault of the drive-by-wire. It may just be that the engine is unhappy.
Yeah, I think that's a really valid point. And I mean, this really goes for cable throttle as well. It's something that I've sort of drummed in over the years with our webinars when we've been talking about transient or acceleration enrichment, getting all of that right. And a lot of people will try and fix a transient enrichment problem or a perceived transient enrichment problem with acceleration enrichment settings or fuel film as it is in the M1, where the underlying issue may actually be more around the zones that we're actually accessing at that point in the efficiency table have not properly been calibrated in the get-go. And some of that's tricky because some of those areas are difficult to get to on the dyno, correct? Very, very light overrun areas?
Yes. These are kind of things that you have to look at through data and post running in the track. And then a lot of things that people kind of take for granted is fuel timing. A lot of people kind of just shove it under the rug that the fuel timing isn't that important, but depending on your injector and the port design of the engine, it can make or break your transient fueling.
Okay, that's interesting. It's something we haven't really discussed before. So, what's your philosophy on dealing with that? How do you go about dialing in fuel timing for transient response?
Really, it's about what the engine likes, how it sounds. The Lambda gives you an idea of what's going on, but it may not always give you a 100% representation of how fast the engine is accelerating. Maybe the Lambda is looking a little rich on tip-in, but the engine is accelerating great. or maybe the lambda isn't going as rich as you expect. So you kind of look on a port injected engine, you kind of look at closed valve injection versus open valve injection and deciding whether or not your injector plume is okay enough for open valve injection, or if you should rely on boiling the fuel off the valve.
Okay, we've got another little rabbit hole to dive into there. So closed valve versus open valve injection, just to clarify, I mean, it is a real big hint in the name. Timing the injection of that fuel from the port injector as to whether it's going to be injected when the intake valve is open, which on face value seems like what we'd want to achieve. We're getting the fuel going straight into the cylinder. Closed valve, on the other hand, we're injecting that fuel onto the back of the closed intake valve. Now, where we can get benefits from that closed valve injection, though, is the heat of the valve, the intake port wall, tends to vaporize that fuel off so that when the intake valve opens on the next cycle, the fuel's actually ingested in a vapor form, which is really, really nice and easy to combust, versus if we're shooting an atomized mist of fuel into the cylinder, I mean, it might not burn as easily. Is that correct?
Yes, and you, with the closed valve injection, you get to take better advantage of your, like we spoke on earlier, your latent heat of vaporization. Sometimes you get a better cooling effect from that. And the open valve injection, depending on your injector, if it doesn't atomize very well, you might just be spraying a lot of liquid fuel that the engine will be quite unhappy with in terms of compressing and combusting.
I think what you mentioned as well earlier with the lambda, again, it sort of matches my experience. I kind of, a lot of tuners, I think, try and live and die by the air-fuel ratio reading when they're tuning something like acceleration enrichment. And I'm always more of a case of use it as a guide, but really what's important is the crispness of the result. Is the engine cleanly blipping, accelerating, doing what you want? If it is, then I'm less concerned about the absoluteness of the lambda value. And it sounds like that's exactly the same approach you're taking. So, all right, we've talked here about the latency or lag, the safety. Basically debunk both of those as being issues. So let's get back to the actual sort of crux of the conversation, which is around that throttle blip. So, for a start, how do we know how much to blip the throttle? What's involved with that? Do we just give it a 100% blip, or are we trying to maybe match some data from a manually shifted car and seeing what the driver's actually doing?
If you have access to that data, it's pretty useful. But for the most part, you want to start a little aggressive, in my opinion. I wouldn't say 100%, and it really depends on the inertia characteristics of the engine. Because not only are you commanding a position, but you're also commanding a time. So in the M1 strategy, for example, you command a blip at the throttle. Let's say you blip to 80%, followed by a hold phase where the throttle is held at a slightly lower value, maybe 40%, where you're trying to fill the plenum with air and prepare it to be able to re-engage the gear set.
Now, on face value, blipping at 80% might seem like an over blip. And I mean, ultimately what we're really trying to do here is match what the engine RPM should be in the next lowest gear. But there are gear ratio tables in the ECU. It understands what the shift is going to be, and it can calculate what the RPM should be in the lower gear. So one of the strategies that the MoTeC employs is we can essentially use a really aggressive blip, or what would result in an over blip, but then introduce a fuel or ignition cut, basically a rev limiter at that calculated RPM for the lower gear, correct?
Yep. So that's what we would call engine speed matching, where you enable the ECU to calculate the expected engine speed from the following gear and allow you to run an excessive amount of blip, and the engine will come up and hit that limiter and allow you to do an ignition cut or fuel cut to match the engine speed. And that lets you run that aggressive blip.
Which is also not uncommon. I mean, if you listen to a GT car going around a racetrack on the downshift, you'll hear that crisp crack, which is essentially that limiting activity, correct?
Yes.
On that basis, is there any reason why we wouldn't use that engine speed matching mode and essentially run, well, I guess we'd call it open loop?
So again, in terms of sensor failure, if your blip is too aggressive, and then you have a sensor failure and you no longer recognize barrel position, the ECU will have a hard time working around, because you're then relying on an estimated gear position based on front and rear wheel speed, which may or may not always be fast enough to deal with the gear shift itself.
Okay.
So you can run in a situation where you over rev the engine.
So, I mean, really, it's just like any other element of tuning. It's not a band-aid for doing the job poorly in the first place. It's not like, it's no different to maybe using closed loop fuel control to clean up your shoddy efficiency table, and if the lambda fails, then all of a sudden you've actually got some really, really poor fuel tuning. So same thing with your blip.
And I think that's important to just understand about all closed loop tuning, and all, even now with the addition of learning and adaptation, that you want to do your best to maintain your open loop tuning. Want to make sure that everything is within reason and not heavily lean on the closed loop. Now, you can use it as a tool to expedite that process, come in with an excessive blip and then kind of figure out where your blip needs to be. But you can come in excessive to make the downshift happen.
Yeah. I mean, I think that's something that a lot of poor tuners out there are relying way too heavily on the closed loop control strategies. And I'm talking more here around maybe fuel and knock, to pick up the pieces after they've done a poor job. But I mean, my strategy has always been to get everything as good as it can possibly be. So we're leaning as little as we can on the closed loop strategies, and then the closed loop strategy doesn't need to do as much work. We're generally almost always going to get a better result, even not considering for the moment what happens if that closed loop strategy actually fails. All right, so the element you mentioned earlier about manifold pressure, so this can also be a driver on how crisp our throttle blip is. And I've talked with one of the techs at MoTeC Australia in some length about some of these elements, and you've got the ability to have a minimum throttle position table in the MoTeC to help with the shift as well. And I'm guessing what you're basically doing there is limiting versus RPM what the throttle body opening will be. So that has an element of controlling what the minimum manifold pressure will be. It's going to have an element of affecting the feel to the driver in terms of engine braking effect, and it can also affect the blip, correct? Can you talk to us about those elements a little bit and how you go about tuning that table?
So a big part of the manifold pressure is that you want to make sure that the plenum has enough air mass so that when you go to reintroduce torque, that there's something that the engine can feed off of and almost drive the car away, but not too excessively. If you on a turbocharged engine, for example, if you pressurize the plenum too much and you go to reintroduce torque, the vehicle will almost jolt away with the driver. And, that messes up the driver's line and it upsets the car. The engine braking side of it is more so important, especially on, let's say, like a motorcycle, where on a MotoGP motorcycle, for example, the engine braking quite defines the drive line for the rider. So that throttle position, that minimum throttle position, and how much you let the engine either act as a vacuum pump or act as a free-flowing pump dictates how the rider may ride the bike.
From what I've sort of learned talking to various engineers, calibrators, as well as drivers, a lot of that also in terms of the engine braking element really does come down to a personal preference in terms of the driver, or you mentioned their rider, in terms of how they want the car or bike to feel under braking. Is that reasonable?
Yes, it's 100%. Because it's either going to build or decrease the confidence the driver may have in the car or the rider may have in the motorcycle.
Yeah, it really comes down to a lot of the world of calibration, unfortunately, is not necessarily black and white, but is shades of grey. So it's important to understand there isn't a one-size-fits-all solution that we can apply across the board and call it good. You can get a baseline, and then from there, it's iterative changes to get all of that dialed in exactly how the car, the gearbox, the engine, and the driver actually want. So coming back just one step to that point about the pressure in the plenum, basically what you're saying there is if you've got the throttle closed hard up against the stop, basically as low as it can, as closed as it can be, you can end up with such a low manifold pressure, essentially a very limited amount of oxygen in the plenum, so that when you initiate that blip, there's not enough oxygen really, or enough air available to combust initially, so that in and of itself creates a little bit of latency with the blip.
Yes, it'll create latency with the blip, as well as latency in the reintroduction of torque phase. When you go back to let the engine run again, you could come in a situation where the engine is feeling bogged because you don't have that air mass for the engine to feed off of.
All right, again, it's been a very tech-heavy chat, but I wanted to get into this because it's not often we get a chance to dive into this information with someone who's had so much experience with it. So we really do appreciate your input on it. Last element on this topic, just in terms of the calibration process, what are you relying on? Are you doing this on a rolling road style chassis dyno? Are you calibrating it on the road or the racetrack, or are you relying on data analysis post session, or all of the above?
So my personal preference is to not tune road race cars with paddle shift on the dyno. The dyno doesn't, in my opinion, represent the track surface, because the way the chassis reacts on a chassis dyno is not the way it will react on a track surface. On a chassis dyno, you're strapped and you're loaded against a rolling mass, and the vehicle may bounce back and forth against a rolling mass. You'll be chasing your tail, because then when you take it to the track, it's going to act totally different.
So track or data analysis, or a combination of the two?
Yep, a combination of the two. So normally, the way it would work is when you would do systems check on the dyno, make sure it shifts, make sure the actuator works, make sure you got air pressure. Take it to the track, send the driver out, have it shift, come pull data and make changes. And it kind of becomes an iterative process after that.
Given the fact that we're talking about a process that is happening in literally milliseconds, I assume that logging rate here becomes a fairly important element. What sort of logging frequencies are you looking at for those key elements of the gearbox calibration?
So the biggest one is the barrel position. You normally log that, let's say 500 hertz, because you want to be able to identify if you have any dog-to-dog events. You want to be able to see how soon if your preload is actually loading up the barrel. So you can see when the actuator, even though you may be commanding 15 milliseconds of preload or something on the actuator, you want to verify where the actual movement of the box starts to happen.
All right, let's move on. Just briefly, what I wanted to talk about, because we haven't really touched on it, is what you are offering as Zelaya Brothers in terms of the services. So obviously, calibration's a big element, but you go a bit above and beyond this. So what other services are you offering to your customer base?
So product development is what I would like the company to be focused around. We recently did a plug-and-play kit for another MoTeC dealer for a third generation Hayabusa. So Suzuki actually came out with an update to the Hayabusa chassis and, gave it drive-by-wire, gave it some CAN bus, more complicated gauge cluster and stuff like that. So we came in and did some reverse engineering, developed an enclosure, a circuit board, and kind of put together a plug-and-play kit that now that dealer can install for the customers in tune, and we just provide support directly to the dealer.
What about sort of the development of EVs? I mean, obviously it's early days in terms of the aftermarket, but we are sort of starting to see it gather a little bit of momentum. Is that an area that you're looking to as well?
We're looking into it. I'm close friends with Sasha, who you've actually had on your podcast, and we've discussed some stuff before. It's still in its infancy, I think, a little bit in terms of the aftermarket and kind of what that might look like in terms of integrating all these different modules using, say, an M1 as a vehicle control unit, where the M1 will act as a communicator between a lot of these different modules and a torque handler almost, where it will manage where the torque is going. Right now, there's a lot of archaic solutions that people are getting by with, but for the serious players, they're looking into applications like MoTeC and Bosch.
Yeah. We actually, as you mentioned, we've had Sasha on the podcast, and we are actually working with Sasha to develop a fundamentals course on electric vehicles, because we see that is going to become more and more prominent in our aftermarket industry, particularly as the availability of components and the price of those components comes down. The sort of EV conversion, I think, is only going to gain more and more steam. All right, I think we'll move towards wrapping this up, Oscar. And we like to finish our podcast by asking our guests the same three questions. And the first of those is, what's coming up for you and your business in the future? I mean, obviously, still a very young enterprise. You're obviously still very young yourself. Where do you see this going? Give us your sort of 5 to 10 years sort of horizon, if you could steer into your crystal ball.
If everything were to go perfect, we would like to develop our own hardware. Probably the first set of that will be a DCT controller that we're looking to get into that field as more and more people try to adapt those gearboxes. I think it's a good first stepping stone into some major product development.
Yeah, I've talked in the past with the likes of Tony Palo, who's a big player in the R35 GTR community, and about the limitations when you are stuck with a factory transmission control module. So, standalone done right definitely would have some huge potential. I mean, there's still tables in those GTR transmission control modules, as I understand it, that people don't really know what they are. They're not defined. No one really knows how they work. And I think complete control, obviously, a lot more flexibility in there. Now, our next question. This is a tricky one for me. We always ask our guests, given your experience and where you've got to in the industry so far, is there any advice you'd give to a younger version of yourself? You're 25, you're still pretty young, but maybe for those listeners who are still in college looking at starting their career, even in the time you've been doing this, you've achieved a lot. What would you say you've learned that you could pass on?
I would just remind my younger self, I think when you're young, it's easy to get really proud. You may help somebody who has a really big name in the industry and you might feel really, really good about it. But, just stay humble. Everybody's always learning. Just because you know more than this person on a particular topic, maybe you're just more fortunate to be exposed to that topic at a different time in your life versus that other person. So everybody should always be open to learning.
Yeah, I think that is excellent advice. The stay humble thing in particular, it is very easy, particularly when you start achieving some level of success in some area, to start maybe getting a little bit too big for your own boots. And normally I find when that happens, you pretty quickly get cut down to size. It's just always important to understand that this is a massive industry. There's a huge amount to understand, and no matter how good you are or how good you think you are, there's probably almost certainly someone out there who knows a hell of a lot more than you. Lastly, Oscar, if people want to follow you and see what you're up to, get in touch, how are they best to do so?
Most of what we post is always on Instagram at Zelaya Brothers. That's where most of our updates are. We also have www.zelayabros.com. That doesn't get updated too regularly yet, but that may change in the future as we grow.
Cool. Now, again, as usual, we'll link to those accounts in the show notes to make it really easy for people to find. Look, Oscar, a great convo, really great information. I appreciate your time today, and my hat off to you on how far you've come at such a young age. It obviously bodes well for your future, so we wish you all the best and all the success in your future.
Thank you very much, and I appreciate the opportunity to be a part of this. And a lot of people in the industry appreciate what you guys do. It's expedited a lot of exposure in the industry, so that's awesome.
Excellent. Oh, thanks for the feedback. We like to hear that. All right. Thanks again. If you enjoyed this episode of Tuned In with Oscar, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to George Bill Fred from the US, who has said, I've searched for automotive podcasts that provide in-depth technical info and have had a tough time finding any. This podcast has given me what I was looking for. Andre does a great job of going back and unpacking the data that guests provide instead of moving on and leaving it at face value. The wide range of guests is also a treat, from engineers to tuners and race drivers. I look forward to them each week. The only suggestion I would give is to make them long longer. Oh, George, thanks for that feedback. Glad that our podcast is hitting the mark with you. The length thing is a tricky one. We've tried to keep a balance without sort of taking up too much of our guest time, and I think for the most part we're trying to hit that mark. But obviously we can't keep everyone happy, and some of our podcast guests we could have probably gone a little bit longer with, so I'll take that on board. Anyway, if you can get in touch with your t-shirt size and your shipping details, we'll fire out a fresh tee straight out to you. All right, that concludes our interview, and before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpaacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpaacademy.com/courses.